Okay, welcome to session 9.1, or as one of my students calls it, season 9, episode 1. Since you saw me last, I competed as I often do. I compete in, uh, as a hobby, speed skating races, short track speed skating. Mainly got into it because of my son. Actually, you can see, look over my shoulder. You can see my son. It's a picture of my son and another picture of me right next to my son. And unfortunately, went into a turn, and just before the turn, I thought, I got to do this like Apollo Ono. And next thing I know, I'm on the ground, and I broke my wrist, and I got four. Where is it? Which side? Four stitches right here and a black eye. But I'll mend soon. Okay. The worst part, it's going to be hard to write. That I'm right-handed and hurt my right wrist. Okay, but we're going to go back. We're going to talk about McKelvey-Palfrey paper, the quantal response equilibrium. Okay, here is where we left off. We had the Ox game, OCHS, I think it's 1994. It's cited in the McKelvey-Palfrey paper. That game, as you recall, is very much like the matching pennies game, except what we did is instead of putting a 1 there, like the classic matching pennies game, we put a little higher number, but 4. And Ox ran some experiments, find out, how would real subjects react. And we found last video, I discussed some differences from what the mixed strategy Nash equilibria predicts. So what we're going to do is we're going to look at the technology from McKelvey-Palfrey that tries to predict those deviations that we see in this game and many others from what the Nash equilibrium predicts. Okay, first thing, let's go back to some technology. Okay? Now I'm gonna now McKelvey-Palfrey they do this more in a more general setting, but I'm gonna apply all their definitions just right now to the Ox game. Okay, now McKelvey-Palfrey they talk about the scene utility. Okay, think back to the McFadden paper, where the scene utility is what the researcher knows. Then there's this error term that we call random utility, which the subject knows, but not the researcher. Okay, we'll add a little bit to this when I say the unseen utility. It's going to be something that neither the researcher nor the other player knows. So the key thing is we're now in the world of game theory. Everything before had been decision theory, so now we have two players. So we have we have the researcher plus two players. So we have player A, say, knows his own error term, but the researcher, the researcher, does not, nor does player B. Okay. Now, so U bar, that's going to represent the scene utility. In an experiment, what that means is that's just the money, the money that the experiment, the researcher pays to the subjects. Okay. Now that's a little bit different because what we're going to do in this game, we're going to say that that maybe B randomizes instead of playing the payoff would depend on A's payoff will depend on B's strategy. So let's say for the moment that B is randomizing. He's picking a probability P sub B as the probability P sub B1. It's probability that he plays B1. Okay, now later, okay, as I mentioned this, here's what we're going to do. Eventually, what we're going to, I think the best way to think about this is there's a PB1 and then probability plays B2 is just 1 minus PB1. Okay, there's going to be something similar for player A. Player A is going to have PA sub 1 and then 1 minus PA sub 1. Probability plays A2. The P's, think about them as if the equilibrium god announces what these P's are. So the first, the equilibrium god says PB1 is something, PA1 is something, and then the players react optimally to those. So player A, assuming that player B is actually going to play what the equilibrium god announced, he eventually is going to say, "What's my best? What's my best response? What's the optimal way to me to respond?" And that's going to be a probability which we'll call sigma. Sigma sub A might not equal P sub A, but if it's an equilibrium, that's what we're going to look for. We're going to look for a P sub B sub 1 and a P sub A sub 1 such that they equal the sigma A sub 1 and the sigma B sub 1. So if we can do that, if we can find that the P's that do that, we've found an equilibrium. Okay, so we'll get to that in a second, the sigmas. Okay, for now, let's look at the scene utility. Okay, so for player A, he's thinking, well, the equilibrium god said PB1, whatever the value is, and then if player B plays B1, okay, A says I get a payoff of 4. Say it's $4 in this experiment. Now, my expected payoff is 4 times PB1. Now, on the other hand, if B plays B2, I get 0. So 0 times 1 minus PB1, that's probability he plays B2. Okay, so U bar A1, okay, if we delete that term, it's just 4PB1. U bar of A sub A2. So there's expected utility from playing action A2 is, well, it's PB1 times 0, so it's 0, plus 1 times PB2, and PB2 is just 1 minus PB1. Okay, so we got that. All right. Now, here is what we're going to do next. We are going to do what I call the McFadden trick. Okay, we're going to say what's the probability that A plays A1, and the answer is we're going to add some other utility. First thing I'm going to do, I'm going to erase the bars, and so I'm going to put hats. Okay, a bar is the scene utility. U bar is the scene utility. U hat is the total utility. So it's the scene utility plus an error term. Okay, so that's what I'm going to do now. So erase the bars, put in a hat. Okay, when I put the hat on, I add an error term. This is the unseen utility, and so it's epsilon A1, and then the error term for action 2 is epsilon A2. Okay, now I mentioned this I think a little bit last time. Notice that I'm putting the error term. It's an error term involved with the action. Okay. It's a little bit unorthodox, okay, and I think a lot of game theorists would say that that's breaking the rules. We get utility out of outcomes, not actions, okay? So if we were going to do this right, they would say the orthodox way, we would have an epsilon A1, B1, an epsilon A1, B2, an epsilon A2, B1, epsilon A2, B2. So we'd have, instead of 2 error terms, we'd have 4. Okay, so I told you that when you do it that way, and that's what Bresnahan and Reese did. When you do it that way, you get a mess. You really don't get any results. Okay, and kind of part of the genius of McKelvey-Palfrey, you realize, okay, let's do something slightly unorthodox, but at least it gives us some results. Okay. So, I give them a break. I say, if you want to criticize them, I don't. Okay. But here's what we have. Epsilon AA2. Okay, now section 1 of the paper keeps these epsilons general, doesn't assume anything about the distribution, except I think mainly some basic things like maybe infinite tails and that it's continuous, something like that. But from after section 1, they want to start getting some elegant, simple results. What's the best thing to assume about the error terms? Okay, you should hit pause right now. You can answer that question. What should we assume about the error terms? Okay, assuming you're back after hitting pause, the answer is let's do the McFadden trick. Okay, and let's assume that they are distributed Weibull. Okay, now think McKelvey and Palfrey, even though they're both older than me, I think they said extreme value. A type 1 extreme value, which same thing as Weibull, okay? But once you do that, once you make that assumption, okay, here's what you get. You get that the probability that A plays A1, okay, and this is a function of, we don't see PA right now, but we see PBB1. It should have PA, comma A1 there too. Okay, this is, okay, now let me back up. So if we have these error terms, okay, we assert that player A chooses A1 if and only if U bar A1 is greater than U bar A2. Okay. Now that's true if and only if this is greater than this. Okay. And from McFadden, if we know that these error terms are distributed Weibull, that probability, the probability that U bar AA1 is greater than U bar AA2 just equals, okay, let's see if I'm going to have enough room. I don't think I will. It equals, no, you know what it does. I think I will have enough room. It equals E to the scene utility. That's what I call the McFadden trick. 4 P B B1. And that's divided by E to the scene utility of the first choice, 4 P B B1 plus E to the scene utility of the second choice, and that's this. 1 minus P B B1. Okay, so that's it. Sigma A, A1 equals this. The probability that A plays A1 is this. Okay. Okay, what's the next thing I want to talk about? Now, okay, let me explain this. Now, that's not quite right, okay? And I'm going to add something, a term to this, okay, to say what McKelvey and Palfrey do. What I've done here is I've assumed these error terms are standard Weibull, okay? It's not quite saying that the standard deviation is 1, but it's something like 1, I don't set it to just sigma and then estimate sigma. So I've set it to a particular value. I've assumed that these error terms have a particular standard deviation. Okay. Now that's a little uncouth because and you can cause problems. So what it does is if we change the units of the payoffs, that's going to change the probabilities, and that shouldn't be, okay? So, for instance, suppose Ox paid in dollars, so $4 to A if you get that outcome, $1 to B if you get that outcome, and so on, okay? Given that, and given my assumptions, this is the probability. But what if we just change the units to pennies? Okay. So what that would mean is that this all of a sudden instead of 4 should be 400. That should be 400, and this should be 100 times this term. So that's going to change the probabilities if I just change the units. And so that's a problem. So and the idea is that we started off. I'm assuming that the standard deviation of these epsilons is about $1. Okay, but when I change this to pennies, I'm basically keeping the standard deviation of epsilon, or making it 1 penny. The standard deviation is 1 penny, but that may not be what's true in in the actual experiment. It may not be that these subjects, that their error terms have a standard deviation of 1 penny. We don't know what it is. We set it to some value, um, but we basically, here's what we're going to set it to 1, but then we're going to change the units to fit that. Okay. I'm not sure I'm explaining it that well, but here's a way to do that to avoid that problem. Okay, so the idea is that this assumption that the error terms are standard Weibull, um, you can't make without loss of generality. Okay, that's making assumptions about what's really going on with these players. Okay, to avoid that, what McKelvey and Palfrey do is they say, well, we're just going to keep that the standard. We're going to make that standard Weibull, but instead, what we're going to do is we're going to add a lambda to the money payoffs. Okay. And once you do that, then it is you can make that assumption without loss of generality. It is okay to assume that the epsilons are distributed standard Weibull. Okay, and here's an example why that's true. So suppose you've done that. Okay, we've assumed epsilon standard Weibull. Now, suppose we did that same thing I said. We changed the units from dollars to pennies. Okay, if that happened, now, okay, we would change the 4 to 400. Okay, we'd change here the 1 minus to 100 times that. It turns out when we estimate lambda, all that would happen is the new lambda would be 100, would be the old lambda divided by 100. Okay, so if we change the units, all that's going to do is change the value of lambda. Okay, so the key is that when we add this lambda, it is okay to assume that these error terms are distributed standard Weibull. It's no longer uncouth to do that. And we say we can assume without loss of generality that these things are not just Weibull, but they're standard Weibull. Okay. So that's what we do, and that's one of the reasons why we have to add the lambdas. Okay. So I think I've gone a little bit. How long have I gone? 18 minutes. So I'm going to end there. Okay, that was 9.1. See you in 9.2.